Okay, let's get started. I mean, I guess you could do the problem 2 times in 2 different ways. Maybe try to do it. No, I'm kidding. Yeah, give 2 proofs, or give 1 proof and 1 counter. Okay. Okay. So compactness, right? We're doing compactness, compact sets. Somebody give me the definition of compactness. Tell me what compactness means. Right? We say a set is compact if blah blah blah. Right?
Can we define it in such a way that if the set is both bounded and closed?
No. No. So it is true that in Euclidean space we will see that compactness is equivalent to being closed and bounded. However, that's not true in the general space. And so compactness is not, if you said, oh yeah, compactness, which means closed and bounded, they would say, who is your teacher? And I'd be laughed off the face of the earth. So, yes?
For any open cover, there is a finite collection of subcovers that covers those.
You said it a little bit, not exactly right, but so for any, K is compact if given any open cover G alpha of K, right? Given any cover, right? Any open cover. Remember what an open cover is? It's just a bunch of open sets whose union covers K, right? Right. I.e., the G alpha are open. And the union of the G alpha contains K, right? Okay, so given any open cover, there exists a finite subcollection, right? Of the finite subcollection, G alpha 1, G alpha 2, G alpha n, say, of the G alpha, right, such that this finite union, right, G alpha I from I equals 1 to n contains K. Okay. So given any open cover, and for this to have any meaning, it should be some infinite open cover, right? So given any open cover of K, there's a finite subset you can choose. There's always going to be a finite subset that still covers the set, still covers K. Okay. Okay. It's hard to show things are compact. It's easy to show things are not compact. Or it's easier to show things are compact.
So you mentioned that it has to be an infinite open cover, right? That only makes sense.
I mean, if it were finite to begin with, then you would be done, right? There's nothing to check, right? They'd say, well, what finite subcollection are you going to choose? You're going to choose the whole collection, right? So there's nothing to be done there. Yeah, that's right. Okay, so let's give some examples of things that are not compact. So Z is not compact. Right? So to show something is compact is hard, right? Because to show something is compact, you have to show that for every cover, you've got a finite subcover, right? To show something's not compact just means you have to find one cover for which there is no finite subcover, right? Everybody follow that? Right? To show something is compact means that you have to show every single cover has a finite subcover, right? But to show something's not compact, all you need to do is find one bad cover that doesn't have a finite subcover. Okay, so here is Z, right? Right, here is Z. And to show it's not compact, all you need to do is find one bad cover that doesn't have a finite subcover. Well, what bad cover are you going to choose? Turn to your neighbor and tell them what bad cover.
But don't have to find colors, like the function is finite, because I guess if you have an outcome curve, you can go to like minus biggest element.
Okay, so what bad cover have you hit on? Who would like to give me an example of a cover that doesn't have a finite subcover? Anybody?
Maybe end to end.
End to end? Okay, sure, you could do that. You could say, okay, I'm going to take G sub n to be the interval negative n. Right? That's a good one. Because if I take the union of these guys, these are open sets, the union of them, gradually cover the whole set. But I can't take any finite collection of them. Any finite collection of them will just cover the, I look at the largest n, and then I cover that interval of radius n, and that would be it. Okay, so that's a good one.
Can it be minus infinity to infinity?
As what? As your,
As Gn, G.
as like G1 or something like that?
Yeah, like there's no, it's just like based on the same premise of the previous example.
Okay, so I'm gonna also throw in G infinity, which is negative infinity to
Yeah.
infinity. In other words, the whole thing.
Yeah.
Okay, that would not be a good example because it wouldn't show that this is not compact, right? Because to show something is not compact, you have to find a set for which there is no finite subcover that covers the whole thing.
Yeah.
Okay, but if you threw in this guy, you could choose a finite subcover. You'd say, okay, I'm going to choose that one guy, right? And I've covered the whole set. So that would that wouldn't satisfy what we're looking for, right? That doesn't satisfy
Oh,
the
because
parameters.
that's the open cover, okay.
Yeah, we're trying to find something that shows that this is not compact. But if you throw that in, we have no idea.
Yeah.
Yeah. Okay, so that's one example. Did anyone come up with some other examples? Yeah, Max.
You could have the set of all neighborhoods of every element of Z with like radius 0.5.
Okay, yeah. So you could say cover each, let G for each P in Z, let G sub P be the interval of radius a half around P. Okay. Take the interval of radius a half around P, where P is for each guy in your set. Right? So where P is in Z. Okay, so you've covered each of these guys with some with an interval of radius a half. Okay, right. And then the union of these guys is the entire set, but if you take any finite subcollection of these, well, you're only going to cover those finite numbers, right? You're going to cover those finite P, but there are infinitely many P, and so we can't do them all. Okay, so this is not compact. Okay, maybe that's enough. I guess did we do this one last time? 0, 1. Did we do 0, 1 in class last time to show that this is not compact? It is not compact. Do we do it in class? No. Okay, let's do it. So think for a minute. Come up with show me that you can find one bad cover for which there's no finite subcover. Some people stuck around after class, and I think we did this after class. Were you, did you stay after class? Did you see this after class?
On Friday?
Yes.
I wasn't here.
Oh, okay. Are you sure? Okay, yeah. You weren't even in this area. Okay, yes, go ahead.
How's 1 over n1?
1 over n1, that's great. So 1 over n, so let g sub n be the interval 1 over n comma, right? Where n goes from 1 to infinity. Okay, and you see that that you've got this interval 0, 1, right? 0, 1, and you take the open interval. G sub n is going to be the open interval from 1 over n to 1. Okay. Then, no matter, as n goes to infinity, you cover every single point in this open interval, but no finite collection of those is going to cover the entirety. Okay. No finite collection of those is going to cover the entirety. Yeah. All right.
Kind of similar to what Lana had asked last time. What if we took the subcollection where n is infinity?
Well, so you're going to throw in also the interval 0, 1?
Like, isn't that in our set? Because we have n going from 1 to infinity?
No. I mean, when we say from 1 to infinity, we don't actually mean that you actually put in an infinity there. Yeah. Yeah. And if we, it just means n is in the natural numbers, right? We don't actually say n equals infinity. And again, if we threw that guy in, then that would sort of ruin the example. Right? We wouldn't be showing. We wouldn't be able to show with that. That would not be a bad enough cover. Okay. So I hope you are getting some sense of what it means to be not compact. And maybe that gives you some sense of what it means to be compact, but I don't know. That's a little tricky. What is compact is a little bit more hard to understand. Okay, so we're in this class, and maybe even the next class, we're going to do a bunch of properties of compactness. Okay, the first one is that compactness doesn't depend on the embedding space. That is to say that, you remember when you had something like a set sitting inside some set, sitting inside some larger, sitting inside a metric space, sitting inside another metric space, then you could have something that was open relative to this guy and not open relative to that guy, right? But that won't happen for compactness. If you're compact relative to x, you're compact relative to y, and you're compact relative to y, you're compact relative to x. Okay, so you don't have to say compact relative to something. You're compact. Okay. Okay. So compactness is not relative. Okay. So so you have some set K that's sitting inside some space y, sitting inside some space x. Then, so I'm going to say it now and only now. K is compact relative to y, if and only if it's compact relative to x. Okay. Okay. So I'm only going to prove half of this because the other half is basically the same. Okay. So say K is compact relative to x. Okay. So it's compact relative to the larger space. Okay. So in your head, you've got y here, you've got x here, your bigger space, and you've got some k sitting inside here. Okay. You've got your k sitting inside your space, and you know that k is compact relative to the ambient space, to the bigger space, and you want to show that k is compact relative to y. Okay. So you think about what that means. So you know that if you cover k with an open cover in x, then there exists a finite subcover. Okay. You want to show that if you cover k with a open cover in Y, then there exists a finite subcover. Okay. What do you know about open sets in Y, X and Y? Well, you have one fact, that an open set in Y is an open set in Y you can get as the intersection of some open set in X down to Y, right? Every open set in Y you can realize as the intersection of Y with some open set in X, right? So you see what we're going to do, right? If you've got an open cover in Y, well, you bubble everything up to an open cover in X. You take use the compact relative with respect to X to throw out all but finitely many guys, and then you intersect back down and you get the open cover in Y. Okay, so that's it. Right? You say, okay, compact relative to X. We want to show that given any open cover in Y, you got a finite cover in Y. So okay, so given a G alpha an open covering of K in Y, well, we know from the previous theorem that each G alpha equals Y intersect some H alpha for some H alpha open relative to X, right? So those are the bubbled out guys, right? The G alpha are sets here, and the H alpha are the expanded, thickened guys. Okay. Okay. Well then, of course, H alpha is an open cover of K in X, right? But K is compact relative to X, and so we can throw out in part of those guys. K is compact relative to X. So we know there exists some subcollection H1, HA1, HAD, say, such that K is contained in the union. Right? But then you just intersect both sides with Y, right? K intersect Y is then contained in HA1 union HAD intersect Y. And that tells you, that K is contained in the union of the HAI intersect Ys. By properties of sense. That's to say the union of the G alpha i's from I equals 1 to D. Right? Okay, so K is covered by some finite subcollection of the G alphas, right? And so K is compact with respect to Y.
So it's going backwards, right? The proof's going backwards?
Oh, do I have the wrong direction? Yes. Sorry. That's why people look confused, I hope. You guys look more confused than I thought you would be. Yes, Susan.
Is that alpha, H sub alpha, alpha?
That's a D.
Oh,
Yeah. This is alpha, this is a D.
okay.
I try to make them look even more similar. Maybe I can make all letters look the same with some practice. There's that guy who makes words that you have a word that looks one way, and then you turn it upside down and it's a completely different view. Have you seen that?
It's old, yeah, it's like the old phone.
No. He makes I forget his name, but there's a person who will write a word and have it so that when you turn it upside down, it's a completely different but related word, just for making an optical illusion. Yes, Aria.
The bottom line, we say K is contained in the union of the H alpha i's.
Could you explain why we have the third step that K is a subset of the union of H?
This step?
The third,
This step.
About that.
This step.
Yeah.
So remember the idea, right? You start off with a cover. You've got your K here, right? You've got your K here, and you start off with a cover, the G cover, right? The G cover is in Y. Okay, there's infinitely many of them. And I'd like to get a finite collection of them that still cover K. Okay. So what you do is you fatten everybody up. And you say, okay, I know that each of these guys, since they're open relative to Y, come from the intersection of Y with somebody in X, with a bigger guy, with a fattened open covering in X. Okay. So I fatten everybody up. They still cover K, right? So these are the fattened guys, and you've got K, it's covered by K is covered by the fattened guys, but K was compact relative to X. So you can throw out all but finitely many of them. Okay, here they are. Here are the finitely many guys. K is covered by the finitely many guys. Okay, so we're using the compactness here. Okay, and that gives us that K is covered by finitely many of the G's, so K is compact in Y. Yeah.
How do you go from K intersect Y to just K is contained?
Well, where is K?
K is in X.
K is in
In Y.
Y. So K intersect Y is just K.
Oh, okay.
Yeah, I intersected both sides with Y, right? But that doesn't do anything on the left-hand side. Okay. Let's go on. Okay. Yeah, actually, the next one is kind of cool. So, for amusement, I proved the next one in a different way. But I think the different way is nowhere near as cool as the way. Actually, the way that it's proven in the text is very illustrative of how one uses compactness. Okay. Whereas the proof that I came up with is not. I mean, it uses compactness, but it's not as representative. So, so this is a pretty cool proof. You've got K sitting inside of X. X is a metric space, right? And K is a compact set. So, K compact forces K to be closed. Okay. So you might, if you felt like it, try to prove this directly by saying, okay, we want to show that K contains all its limit points, right? Suppose K doesn't contain a limit point. Well, then blah 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 blah. And you can make a proof along those lines. But far cooler is to do this. You say, let's show that K complement is open. Okay. See, here's your set K, right? And you choose some point in K complement. And we want to show, right, that K complement is open. In other words, we want to find a ball that's contained in K complement, right? We want to find an open neighborhood that's contained in K complement. Okay. So here's how you do it. You say, okay, for each point, for each Q in K, cover it. Cover Q with a neighborhood of radius R sub Q. Okay. Cover it with some radius R sub Q where, right, so here is R, no, here is Q, excuse me, right? And the way you create R sub Q is you take the distance from P to Q, you divide it in half, and you let R sub Q be anything smaller than that. Okay? R sub Q will be something smaller than half the distance from P to Q, right? Okay. Where R sub Q is smaller than half the distance from P to Q. Right? And you notice that if I take the ball of radius R sub Q around P, then those guys don't intersect, right? So observe, right, that the radius from the R sub Q neighborhood of P and the R sub Q radius of Q don't intersect. Okay. Okay. So, can anybody tell me the rest of the proof? Anybody tell me the rest of the proof? What am I going to do? Well, I've covered I've covered every Q with such a neighborhood. What am I going to do? This is a proof involving compactness. There's only one thing you can do. Right? You've got an open cover, so you take a finite subcover, right? So, K is covered by these intervals, by these balls, right? Right. So this is an open cover. Okay. So we know by compactness, there exists a finite subcover RQI, Q sub I, where I goes from 1 to n. Yeah.
So for the point P, does it have to be in K
K complement.
complement?
Yeah.
Okay.
Yeah. So we're trying to show that if you have anybody in K complement, then there's a ball around it that's contained in K complement. Okay. So there's a finite subcover. It looks like this. Right? So let me just draw it. Here's another Q, and there's another Q. I can't say. Oops. Right. And I cover that guy with something like this. Okay.
Professor, why are we defining the radius of sub Q to be less than half of the distance?
It is in order for this to happen, that the balls don't intersect each other. And you'll see why that's important in just 1 second. 10 seconds. Okay. So, Thea.
Can you just pick an open cover that's not countable?
Yeah, why not? Yeah, so like just for every point, you choose a set, right? Every point you associate a distance, and you've got this open cover. It's okay, yeah. So yeah, when we talk about an open cover, it doesn't have to be a countable open cover. I mean, compactness means that whatever open cover you have, countable or uncountable, there's going to be a finite subcover. Okay, so so there exists a finite subcover, blah blah blah, and so you see that the union of these guys covers K. Right? The union of these guys covers K. Let R be the minimum of the R sub Q's, R sub Qi. where I goes from 1 to n. Okay. Let R be the smallest radius. Okay. Let R be the smallest radius. In other words, we take the intersection of all these balls. Okay. Right? Then we see that this radius, so this ball around P, does not intersect any of the other guys, right? Intersect these guys is empty, right? Because it's smaller than the guy who did not intersect that guy. Right? Okay. And so, right? So this neighborhood does not intersect K. Right? This neighborhood doesn't intersect K because these guys covered, right? These guys covered K. Right? And so we found this ball that doesn't intersect any of these things that cover K, so we can't intersect K, right? K was inside that cover, right? So this radius, this neighborhood doesn't intersect K. In other words, this neighborhood is contained in the complement, right? And that's the end, right? We wanted to show that K complement was open, and we see that we found a neighborhood of P that's in K complement. Yeah, all right.
Just to clarify, so again, how you went from NRP intersect NRQI QI is empty to the next line. You're saying if it doesn't intersect with any of the neighborhoods containing the QI, then it certainly doesn't intersect. Like it doesn't. None of the QIs are contained in the neighborhoods of P. Is that
Well,
what you're saying?
what we knew from before is that if I made it like this, QI, this guy intersect that is empty, right? But this thing is, this guy, NRP, is contained inside of NRQI, right? Well, the bigger guy didn't intersect this. How is the smaller guy going to intersect it, right? Helen.
I still don't understand why if you pick RQ is less than 1/2 the distance from P to Q, the intersection is empty.
Well, think like this. So you've got 2 points, A and B, right? You got 2 points, A and B, and you take the distance between them, right? And you take half of that distance and you take something less than half that distance, and you make a ball of that radius. Make a ball of less than half the distance, right? Can I have a point in the intersection?
Oh, I see.
No, right? If I had a point in the intersection, that would tell me that this distance is smaller than itself. You can get, if you want, you can do a proof by contradiction. So you can try it as an exercise. You get a proof by contradiction. It would show that this distance is actually smaller than that D is smaller than D, which is crazy.
Okay, thank you.
Yeah. Max.
Why can't you use exactly 1/2 of the distance from P to Q for the radius?
You could. That'll be fine. But I'm just being cautious. Like, maybe I'd say like less than 1 times 10, 1 over 10 to the 10. Just to make it completely clear that you're not going to have an intersection.
Is P a point in K? Or in K complement?
P is in K complement. So remember the line of the argument. We've got K. We're trying to show that it's closed. So we do the opposite. We show that K complement is open. So take some guy in K complement, right? We want to find a neighborhood that doesn't intersect K. In other words, that lies inside of K complement. In order to show that P is interior. Okay. And via this process, we create this neighborhood.
Okay, so we didn't have to define it, but it's like intuitive that P is in K complement.
Yeah, I think I said that P was in K complement here, so maybe I should have written it. So let, yeah, pick any P in K complement.
Thank you.
Yeah. Okay, let's go on. Okay. Next proof, not as cool, but still important. So, if you have some compact set, so K is compact, sitting inside the metric space, right? And you have some F sitting inside of K. Okay. If F is closed, then F is compact. Okay, so any closed subset of a compact set is going to be compact itself. So if I know the set is compact, then anything closed inside of it is still going to be compact. People usually use the letter F for closed because of French. Definitely right, closed. Okay, so we want to show that F is compact, right? So you've got this guy sitting inside. So you've got your space, you've got your compact set, and you've got this closed set sitting inside of it. Okay. You want to see that F is itself compact. So what do you have to do? You need to take an open cover. So take an open cover, G alpha of F. Okay. I forget why people use the letter G, but there's actually some reason for it. It's from some German word. Anyway, so you take some open cover of F. Right? So open cover of F, and you want to show that you can take a finite subcover. Well, what do you have? You have that the bigger set, the set that you lie in, is compact, right? So what are we going to do? We're going to get an open cover of K. Okay, we'll extend our open cover to create a bigger open cover for K. So throw in F complement, right? So add in F complement. So let G G infinity. No. So just think like this, right? So we throw in F complement, right? So notice F complement is open, and that if I have all the G alphas, and I also throw in the set F, this is an open cover. This is an open cover of K, right? I have an open cover of K max.
Wouldn't you be throwing in F complement instead of F?
I'm sorry, yes, F complement. Okay, so this thing is an open cover of K. Well, what am I going to do? There's going to be a finite subcover, right? So we know there exists, since K is compact, we know there exists a finite subcover. Finite subcover, G alpha 1, G alpha n, and maybe F complement, possibly. Right. Okay. So there's some G's, and maybe there's that guy F complement. So that covers K. Okay, but then F lies in the union of the G alpha 1 to G alpha n. I can throw out the F complement because I don't need it, right? I don't need F complement to cover F, right? F complement doesn't intersect F, right? Then F is contained in this, and so we have a finite subcover of F. Right? And you're done. So F is compact. Okay. This proof is pretty straightforward, I think. Any questions? Okay, hang in there. Take deep breaths. Drink some water. I don't know. Okay. Okay, I think we can probably do at least one more proof. Okay, so the next one is kind of an interesting one, and it's important. So you have a metric space, and you have actually a collection of compact sets. A collection of compact sets. Okay, you have a collection of compact sets. If this collection has what I'll call the finite intersection property. Okay, and by that I mean that the intersection of every finite subcollection is empty. The intersection of every finite subcollection is empty. Okay. If it has this finite intersection property, then the infinite intersection of all of them, is non-empty. Non-empty. What am I saying? Is non-empty. Then the infinite intersection is also non-empty. Let me give you an example of a set that doesn't have the finite intersection property. Right? It'll look like, so if I look at, say, 0, 1 over n, if I let k, now these guys aren't compact, okay, because otherwise they wouldn't. Anyway, so let G sub n, let E sub n be the interval of 0, 1 over n. Okay. Well, okay, actually, sorry. Sorry. Let me not do this. I'm not going to give an example because I'm getting off track here. Okay. So here's what we're going to show: that whenever you have a collection of compact sets with the finite intersection property, that is, when you intersect finally many, it's non-empty, then you're guaranteed a point in the infinite intersection. Okay. You're guaranteed a point in the infinite intersection. This doesn't happen for non-compact sets, and that was what I was just about to draw up here. Right? If they were non-compact sets, for example, G sub n being 0, 1 over n, right? Well, you notice these guys do have the finite intersection property, because if I take finally many of them and intersect them, I always get something non-empty. But when I intersect all of them, I get 0. I get the empty set, right? I get the empty set. Okay. That won't happen for compact sets. For compact sets, if you satisfy the finite intersection property, then your infinite intersection is non-empty, right? Okay. So, okay, got 4 minutes. Let's see if we can do it. So the proof is kind of interesting. You say, well, suppose the intersection is empty. Suppose the intersection of everything is empty. Okay. And we'll end up getting a contradiction. Okay. Well, in that case, if I take the complement of the intersection, I'm going to get the whole space. Right? If the intersection is empty, then its complement is going to be the whole space. But the complement of the intersection is by De Morgan's rules. The complement of the intersection is going to be the union of the complements. Okay. And so I cover the entire space with complements of compact sets. Okay. By the earlier theorem, by the earlier theorem, we know that K alphas are all closed. Right? So K alpha complement are all open. Right? Compact sets were closed, complements of closed sets are open. Right? And so we've got this open set, we've got an open covering of the entire metric space. Now, fix any one of the K alphas. And let's call it K alpha naught. K alpha 0. Okay. Well, K alpha naught is covered by the union of all the K alpha complements, right? So we have an open cover. We have an open cover of K alpha naught. Okay. Well, you know what we're going to do. We're going to say, then, thus we have a finite subcover, right? Thus, we have K alpha naught is contained inside of some K alpha 1 complement union K alpha dot 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 union K alpha alpha n complement. Okay. So K alpha naught is contained inside of this finite. This finite cover, finite subcover, right? But then I know that K alpha naught intersect the complement of that is empty, right? Intersect the complement of that is empty. Right? Because K alpha naught is contained inside of that, well, intersected complement must be nothing. Okay. Now I use De Morgan's laws again. I say that the complement of a union is the intersection of the complements, right? So then I get the intersection of the double complements, which will be the intersection of the original compact sets. Okay. So I get K alpha naught intersect K alpha 1 intersect K alpha n is empty. Right? But that's a contradiction because supposedly these sets satisfy the finite intersection property. That is, that any finite intersection should be non-empty. We get a finite intersection that is empty. So that's a contradiction. Maybe somebody can try to prove this directly to give a more illustrative proof. But that's what we have. Okay, that's it for today. I'll send out information about the exam later.